Hi, I'm Stefan, the organizer and host of the emBO++, the next level conference for embedded system developers. Thanks to Zenger, you can check out this video online for free.
So first, thank you very much for the invitation. It's the first time for me. Actually, I tried it a couple of years ago, but for some reasons we couldn't make it. So I'm very happy to talk today a little bit about our view on IoT security, especially on the tension between cyber security and cyber physical security, and give you a little bit some insights of what we do at FISEC and what we provide. And I hope this will be interesting to you as a embedded software community. I probably have only 2 slides, which will be very interesting to you, and the rest is, I would say, some kind of overview or information which are definitely interesting to people who develop IoT products, maybe not so deep for developers. Okay, so what we developed actually during so I have 3 slides for some to explain where we are, who we are, and so we developed an IoT security middleware that is able to automatically assess the security of IoT device. And this means not just the digital security or the crypto, which is the usual case in intrusion detection, but actually the physics themselves. And we use electromagnetic wave emanations and a very tiny radar chip to generate a fingerprint of a device and be able to assess or even prove the integrity of this device. I got lucky during my PhD here in Bochum, the chair of embedded security by Christoph Paar, to one of the first one who developed this technology. But since then, a couple of PhDs followed, and are also members of FISEC. And since then, we got some attentions because IoT is actually growing fast, and some risks are still unknown to some decision makers, and this is maybe something which is also interesting to you. So we come from the Excellence Center at the Ruhr University, which is called Horst Goertz Institute, which is one of the worldwide leading institutes for cybersecurity here in Bochum. We have almost 30 professors just for security and crypto, and the technology we developed comes from there and was also several times awarded, for example, by the ECS or by the MIT 2 times actually. And what is maybe also interesting is that what I'm going to present you was also developed for an application which comes from the Princeton Nuclear Future Labs. Here we are using the technology to prove the silos, so the storages of nuclear warhead facilities, and prove that everything is fine. And this is actually a complicated task because there are 2 parties, they don't trust each other, but they want to digitally prove vice versa the integrity of an environment, that nobody changed something. I have actually a selfish slide here. This is this one. So excuse me that I present this. So FISEC is currently looking for a chapter lead position, a very attractive position, I would say. So if this is something interesting to you or to someone you know, please let me know. This would be a very, very huge benefit for us, and helps us a lot. Okay. So I don't need to say, I would say a lot about IoT. So you know probably that this is something which is growing fast, and there are a lot of applications. I just selected 2 of them, a water meter and a car, like a kind of water meter seems to be a simple environment, but it's actually not. But or let's say it brings already some challenges with respect to battery lifetime, temperature resistance, and so on. And the car, which is a very complex system. And everything in between is something I leave it to your imagination what it means. Okay, when we talk about IoT security challenges, then most people talk about these aspects. So first of all, there will be a huge number of things and corresponding keys. And this is something which is already a big management issue. So proving that the ownership of the keys is only a single entity is very complicated. Most IoT devices are not using asymmetric crypto for whatever reasons. They are still using symmetric crypto only. This is one of the biggest issues, actually, serious issues. And of course, we have the energy constraints, resource constraints, interface constraints, and usability constraints. And this is actually these are actually aspects we need to equally handle to build a successful product. And the usability is, from my perspective, actually the most complicated one. But there's actually I call it level 2 of challenges. And the first one is actually the supply chain. So there are actually different standards to handle the supply chain. For example, if you order some products and you get the products, to verify if the products are okay and nobody changed something on the products or the quality is fine and so on. With the increasing number of devices, this will get a bigger problem. And the second one is this is actually kind of a paradigm shift compared to IT security, and this is the operational environment of IoT devices. So from a security engineering point of view, the security of an object or of an asset or of a device, of an appliance, is always dependent on the operational environment the device is used. So your laptop or your smartphone is secure as long as you own it and you take care that nobody get in touch with it. And this is in IoT environments often not the case. And then in general, the third aspect is that cyber physical systems have several attack vectors. I made it very easy here. Yeah, the first attack vector is the classical cyber attack, where you attack several interfaces, logical interfaces on the device, maybe update features to compromise the device. And this is I would say, far developed. So there are many solutions to solve this or to handle this problem. But the bigger issue is the physical attacks. So what happened if someone get access to the environment where the device is or on the device immediately? So how can we handle this? And for critical infrastructures, for example, as soon as someone get access to a critical component, the component is not trustworthy anymore. And this is then again a cycle. So an unauthorized access to a device, even if it's not the case, leads to a potential compromised device, and we get a bigger problem here. Implementation attacks is actually one of the I would say most interesting attacks. We have several classes here. Classical passive side channel attacks, where an attacker is able to use kind of cheap measurement systems like an oscilloscope and a probe to measure side channel informations like timing information, power consumption, or electromagnetic waves, and perform attacks on this system. And this is one of the cheapest attacks here in the field of implementation attacks, which is one of the issues we are going to solve here, or we want to handle here. I don't know how familiar you are with this kind of text, so I explain it a little bit and bring maybe the example of smart meters. So smart meters, this is a very nice use case. Yeah, so there's a clear business model behind automation of the billing process, maybe advantages like new services of leakage detection and so on. So okay, yeah. So to do asymmetric crypto, we use some algorithms like the square and multiply algorithm, and this is a very efficient one. So it just goes step by step through the exponent and squares every time and multiplies only if there is a 1. And this is obviously maybe something we can exploit. Here you seeing this example, so we can clearly see the square and multiply algorithm from the logical point of view. And then if we go and do some probing on the system, then we can actually see on the power consumption the private keys. Yeah. And okay. Okay, maybe, yeah, so maybe, I don't know, maybe here, yeah. So what I was saying here is that smart meter is a good example why asymmetric crypto will be more important in the future. And one very current example is from the end of February, where the Supreme Court in Switzerland decided that classical meters are not allowed, especially water meters here, because they collect too much data, because the unidirectional communication they're using is not even a GDPR problem, it's even a human rights problem. So it was very interesting, and it will escalate to the EU. And this is less than it's not less. It's 1 month and 5 days out. And this demonstrates again, not a surprise for us, but this demonstrates that asymmetric crypto is super important. Link, please, I guess means Google Switzerland water meter. But I will add a link later in the chat. Yeah. Okay, but this is just an example. Yeah, this is just an example, and I want to show you that that asymmetric crypto is actually important and will be more important in the future, and solutions are required. And doing asymmetric crypto requires actually modular exponentiation, so a cubic complexity with the O notation of the size of the key, which is actually kind of absurdly large things, but are definitely possible with modern embedded systems. Okay, and one algorithm to do so is the square multiply algorithm, which shows us that there are leakages if we implement it in a kind of a non-constant time way. And this is actually done by many implementations. And as soon as we put a probe on it, measure the energy consumption or the wave emanations or even the timing, we will get informations like this. So we see the power consumption and we can actually extract the private key very easy. Yeah? So such kind of systems are is a problem. So asymmetric crypto is not so easy to obfuscate from a side channel perspective, like symmetric key is actually how it's done by classical symmetric key like AES. However, AES is actually also attackable by side channel attacks. But maybe it's also interesting that the biggest patterns with respect to countermeasures of side channel attacks are obsolete. So, no, anyway. Okay. So why do we need physical security? So this is actually a very long-standing and very difficult problem. So extending this kind of theoretical unbreakable crypto from the digital security coming into an environmental security is not solved yet. Yeah? So there are only solutions kind of the military area where they use shields, what I show here in this picture, active shieldings, which measure immediately penetration, but you need batteries. This kind of grid foil needs to be active all the time, and it's actually very unstable against natural environments like humidity, temperature change, and so on. And besides the implementation attacks, where I just showed you an example of the side channel attacks, is Trojan insertion attacks. And this is something which is at least known since Snowden, that this is done by the secret services. But this is also something which is not just important for the logistics or for the transportation of the goods, but also for in-field systems like 5G components, which will be almost everywhere due to the high frequency. The cell size is small, and due to the low latency capabilities, the edge servers. So the things which are done in the cloud are now done on the base station. This will also increase the requirements of physical security of this kind of critical infrastructure components. Yeah, and then there's this interesting Bloomberg article, how China used a tiny chip to infiltrate America's top companies. This is still a very interesting story where I would say several references are missing. But this demonstrates also why the EU and the German government started the so-called SOIS program, a program to provide trustworthy electronics and technology sovereignty. Yes. There was something. Really. I call it no reference. If I say there are no references, then this means there is no really trust in this kind of this in this article. So no references, no citations. Exactly. Okay. However, all these stories have an influence to the regulations. So physical security or cyber physical security is becoming a must-have. This is already mandatory in the TKG 2.0 law in Germany, and also in several other regulations. For example, in the context of smart grids, where requirements to the tamper detection or manipulation of the hardware is coming to the requirements of such solutions. Okay, to handle this, today there are several things done. Yeah, and this is here, I demonstrate a little bit the life cycle of a product from the development, manufacturing, delivery, so all the transportations, acceptance of goods, commissioning, and then actually the operations and the decommissionings. And today, most security architectures are focusing on the operations part. So the system is already in the field, and there's a guard or a fence or a perimeter security, and everything is fine. But the other aspects, and if there is no perimeter security, like in the IoT, these are open questions. The boxes with the red frame, these are maybe the boxes which are interesting to developers and manufacturers by removing ports, by disabling logical interfaces, maybe using epoxide to the entire circuit board, which isn't really a countermeasure, but anyway, but makes it complicated, and maybe use anti-tamper packaging or seals to provide kind of a visual inspection possibilities to such systems. However, this is really kind of a complex chain of different processes and aspects to assess and verify the product integrity, so that you can be sure all the time the product in your hand or you just received is original, nobody modified it, and even in the operations the system is fine.
Wir sind hier in einem kleineren Grossraumbüro.
Bei der Leiter habe ich die Freiheit, dass ich, wenn ich anfange und wenn ich höre mit dem Arbeiten, eigentlich selber einteilen kann.
Overall, how I will do it, it's just up to me, and it gives me a lot of freedom.
Für mich ist die Faszination, mit anderen Leuten einen kreativen Moment zu generieren.
Great colleagues, great environment basically.
It's really nice here and I don't have any issues living here.
Am meisten schätze ich in der IoT Systems, dass wir ein sehr junges Team sind, sowie dass ich auch meine Arbeitszeit in einem gewissen Raum selber bestimmen kann.
And I could merge my life hobby with my office job.
Das Besondere an der IoT System ist sicher die Kultur und die Dynamik, die es gibt in dem Team. Es ist jeden Tag ein bisschen anders.
We have a good organization which will help you to get used to the company in the first couple of months especially.
Das ist sehr interessant und ja, macht mir Spaß.
Standards or solutions in the market are first the SDIP 27 standard. This is a standard where many risk assessments are, the risk assessments are based on the standard, and the standard has 3 zones with respect to the physical proximity to the device a potential attacker can have. Yeah? And this says actually that there are 3 zones, 0, 1, and 2, and this means that nobody is, within this zone. And in IoT, we are immediately in the most critical zone because the attacker often has immediate access to the device, and this brings the device automatically in the highest risk profile, which makes maybe sense for military or whatever systems, but not maybe for a water meter. Yeah? And then there are several other applications or other solutions in the market. One is classical foil seals. So a seal, which is a manual thing, and you can inspect it only visual, and you need a human who's doing this. It's not automatable. Or you have door switches or other switches on the case, which are effective as long as the attacker don't know where the switch is, and as long as the physics and the mechanism of this solutions is very well, and this is often easy to compromise, but still used. And then the tamper-proof enclosures are usually only known for HSMs, so for the core security of PKIs, for example, or for military systems. And by the way, they are very expensive. So there's a standard which includes 300 micrometer penetration needle attacks, and they are very expensive. Yeah. They need huge battery packs and so on. Yeah. If you want to know more about different countermeasures and the ecosystem of securing systems, there's a talk also by us in the Hardware I/O conference. It's publicly available. If you Google enclosure puff, there we will talk kind of 30 minutes about what is currently on the market. Okay, so what we developed is actually a technology which does the digitalization of remote assets from the cyber security part, but this is not the topic today. Cyber security means, of course, all the security goals of confidentiality and so on. But the big advantage here is that we developed a chip, a single chip solution, which includes radar technology. And with this radar technology, we can actually measure electromagnetic fingerprint of a 3D object. And the object can be small, like a cigarette box, and it can be big, like a room. If it's big, we need more chips. And with this radar technology, we extract a device signature, calculate fingerprints in the model, and be able to verify the integrity of the system. Here are some details. So we have two zones, actually, a near field zone and a far field zone. In the near field zone, which can be dependent on the antenna we develop or we use, can be about 10 centimeters cubic. And then we have actually a resolution of down to 60 micrometers, which is less than a hair. And in the far field zone, we have about a 1 millimeter resolution. And FCC and EC compliance and so on. We have a signal processing implemented. So this means we do implement classical logic and crypto on our systems, but we do also implement classical signal processing and stochastical signal processing, which is today called machine learning, on the systems, and perform then several applications. So we perform information theoretical assessments. This is actually only interesting for high security applications, like the warhead example, and also expensive. Today, I would like to focus a little bit on the machine learning aspect, where we have actually two applications. One is the classical anomaly detection, and the other is the state classification. The fingerprinting is more a generic field, which is currently used for experimental applications. But anomaly detection and state classification is actually something we can provide with an API to our partners and customers. So they add the chip into the device. The chip does some initialization and then can actually provide anomalies or states via an API. We have two APIs via syslog and REST. And from the use case point of view, it looks like this. We have a training phase, which can be done at the manufacturer side or maybe in the field side when you install the device somewhere in the public, maybe here a car charging station. This is actually a critical infrastructure component, but very public. And then after we trained it, we do the detection phase. the training phase can be actually depends on the application. So sometimes the training phase is only 5 seconds. Sometimes the training phase is about it's about a month. Yeah. So for example, we do it for ATMs, and ATM is super complex system, and then the training phase takes a lot of time because there are so many moving and mechanical things going on that the training phase takes a lot of time. Okay, perfect. So I have someone who helps me. Michael, perfect, thank you. So there's a post of the smart meters and also the post of the hardware I/O. Yeah, I will say something about the costs. I have a slide to this. Okay. So maybe 3 examples. What we do. The first one is a toy example, and this example handles also kind of this elementary threats. This is a term coming from the BSI, like unfavorable climatic conditions and contaminations, dust, corrosions, and so on. We can handle this kind of things because we teach our system in real time, so in dedicated steps. And this is also one of the bigger advantages. Yeah, so for example, here's a very nice small toy example. We have just a clock inside a box which is installed outside. And there's only the hand for the minute installed. So and the minute is rotating, 60 minutes, one rotation, and we can. Here you can see a little bit the results of the classification algorithm. It's not perfect. It's a little bit noisy here, also due to temperature change and so on. But you can see that even tiny sub-millimeter changes can be detected and classified, and this in a 3-dimensional environment. Yeah, so this means that we try to detect physical attacks by mechanical changes, and this sometimes includes also some kind of shielding material. So we add, for example, aluminum foil or small seals inside the device, but we can assess them automatically with this technology. Yeah. Okay, and second example is unsupervised evaluation of a complex system. Here, an ATM, which is kind of a time-variant physical environment. And then you can see how the algorithm teaches and learns the different states and visualizes the geometric complexity between the geometric distance between one state and another state with respect to this physical environment. And this can be done completely automated. Yeah, so you install the system, you say, please start training, and then you wait whatever time you think all the states are all at least one time established, and then you stop the training, and then you get this kind of result. And then you can maybe tag the different classes with names, and we can also see if anomalies are occur. So if someone adds another system inside the system, like the black box attacks or the cash out attacks on the ATMs. And I don't know if you know it, here inside this ATM, which is a very classical one, this here is actually the log file. Yeah? It's a paper trail log file, what's happening in the ATM. So and they are very common. This is very old technology, very common. Okay. A third example is the product integrity assessment for to provide trusted electronics. So you have the manufacturer, you have unfavorable climatic conditions, and then you have a semi-trusted transportation route and potential threats. And actually the manufacturer as well as the recipient wants to know if the device is actually integer and nobody manipulated it. And this means also that the manufacturer cannot claim that someone else manipulated the device. So this brings also some more trustworthiness to the manufacturer. And here we provide also the API to communicate the fingerprints, or actually the resulting aspects of the fingerprints, for example, to verify the product integrity, but also to do some kind of maintenance things. This is not security related, so I'll not talk about this today, but many of our partners figured out that the technology it's a nice sensor, how can be used as a nice sensor, and they want to do more than just security. Okay, so there was also the question with the costs. So here you see how we started. So actually, we started coming from the research with very expensive equipment, going to kind of cheaper software-defined radios. And since then, we developed commercial solutions. And today, we are offering a commercial solution which is based on our version 2. And this includes also an NB-IoT connectivity and the microcontroller and so on, of course. And in this next version 3, which is already in development and looks very good, we will go below 20 euros. If we provide the starter kit, our chip, actually the version 3 chip, costs between 1.5 and 2.5 euros. And our business model is actually not in providing the hardware. We are actually providing the layouts and the API, the IP, and we are not interested in making some money or some margin with the hardware. This is not something we are good in. This is something the manufacturers and our partners are good in, and we provide this technology. Yeah, so so the device don't need to be in a Feldane cage. So there are definitely differences if the device is inside a metallic environment or a plastic or other materials. This is something we need to handle, and this is also something our system can handle almost automatically. And both versions, like a conductive environment or unconductive environment, has some advantages and disadvantages. To the question, it needs connectivity. Yeah, so our current business model is based on the solution which requires connectivity. We provide also the enclosure puff solution, which is was demonstrated on the hardware I/O solution, which is a local solution, and it is an information theoretical secure solution. So this means the system or the component needs to be kind of stable, mechanically stable. So don't have to change a lot if you use it. And if this is given, then we can use the inside of the device as a key source. And what we do here is we provide something called an algorithmic Tamper proof. Maybe I have some backup slides. 1 second. So what we do is we are using the concept of physical unclonable functions. So we have a physical disorder in the system. We do some challenges using electromagnetic waves and get the response, which is the electromagnetic fingerprint. And then we can create a cryptographic primitive called puffs, which need to provide 3, in our case 4 properties. So of course, the response should not change over time and humidity, temperature. However, the response must change if it's a different device, and it must be unpredictable. So the complexity, the information theoretical entropy of this system must be large. Large means 128 bits. And then this Tamper evidence, so this means as soon as someone drills a hole in the device or open it or whatever, it will also destroy the challenge response behavior. And doing so, you can provide or you can generate something called an algorithmic tamper proof. And to make it very fast, the system generates a key from the inside of the system using the physics themselves. And as soon as someone manipulates this inner enclosure, the system will be destroyed. And here we can show you that the system will be, the key will be destroyed with a hole size of less than 300 micrometers, or let's say about 300 micrometers. And key will be destroyed means not there is one bit changing, that means 128 bits of the key material is changing. And the key material of this system is about 500,000 bits. So 500,000 bits of raw key material, and then we extract a key of 128 or 256 bits. Okay. Okay. So yeah, so we have a starter kit which looks like this. It's in this case a Raspberry Pi 0 with NB-IoT shield and 4 of the sensors, and you can easily use it. Our vision or our vision is that we will be able to provide this technology to the entire IoT by making it even cheaper than €1. Today we are in the field of edge computing, telemedical devices, smart grid devices, and industrial devices. But we want to go, we want to provide this technology kind of a fundamental technology where people don't need to think about, okay, is the risk of the cyber physical security this big? I don't care because it's only 25 cents more and we can handle it. And as I said, security is one thing. For example, in the case of Industrial 4.0, the security is actually not the reason why they use our technology. The reason here is they can handle the warranties and the liability issues. So they know if someone uses the device improperly or gets access to part of the machines where they don't have access, or the access is not allowed. Okay, so maybe again some thing about our team. We are a very nice team, very young, very good in, I would say, what we do. Dr. Christoph Paar, who is the director of the Max Planck Institute for Cybersecurity, is also one of the founders of FISEC, as well as Willy Mannheims. Willy Mannheims, for example, founded Secunet, Escrypt, and 20 other companies in this field, so he has also a lot of experience. And on the operational side, Heiko is my co-founder, and myself, we started the company almost 7 years ago. And since 5 years, we are outside the university and develop the technology to real products. And sorry again, selfish slide. We are looking for a chapter lead, very, very interesting position. Please ping me if this is something you are interested. We would be very happy to increase our team, and I guess we have also very nice offers here. Okay, so that's from me. I have a lot of backup slides if we want to go deeper in the technology or in other aspects. Please do not hesitate to ask if there are questions. Yeah, this is a good question. So the question is if or when does the regulational aspects or compliance aspects from critical infrastructures are going also to the commercial aspects. So I would say that this is something which will happen. So the question is when. So usually we see always a correlation between the security trends from the industrial going to the commercial. However, in commercial, it is very often the case that the devices are in kind of a perimeter secured environment, and this can be just inside the house. And in this case, the risk assessments often don't require such a thing. If we are talking about applications like metering, then it might be not the case. Maybe then there might be some kind of tampering aspects might be important, but this is again something which might also be handled by on the network layer, where you do some kind of plausibility checks with the data, and then you see, okay, this is not normal, we need to check this. So there's no physical security countermeasure on the physical layer required. So I would say in the commercial IoT sector, I would focus on the cyber aspects and less on the physical aspects. And on the critical infrastructure or industrial IoT, there are already regulations and demands who are asking for such kind of solutions. Yeah, and unfortunately, regulations are actually the motivation at the end for our customers. So if we tell them, hey, you need an ECC or a post-quantum resistant crypto, and they say, what do I need? What is the minimum requirement? It's not. It's very seldom that the customers are innovationally driven, and security innovations is something they are deeply interested in. This is this is definitely the case for the security companies we are working with, who are developing really appliances for critis. But for the most manufacturers, they are more handling other problems. Yeah, good question of Andreas. So I think maybe our technology can also help developers to I don't know, to maybe reduce the efforts, or maybe to handle, or the management can handle open risks by having this kind of second layer with the sensing technology. Yeah. So I mean, investing in this necessary practices usually means some kind of time disadvantage maybe in the development. So we see several products or solutions where they are definitely familiar and well aware of the risks. They are still in the product, but they take the risk because they want to be the first on the market. Yeah. Okay. Okay, so maybe to Stefan's question, yeah, so our platforms are usually classical ARM based M-Cortex platforms. So we develop in C, C++, and Rust. And I would say the major requirement we need is experience, because we have good developers. But what is missing at FireSec in the embedded software area today is actually someone who was already involved in larger projects and comes with experience and can teach us how to handle such bigger projects, because we are now getting deeper and deeper in real integrations of our technology into products. So the POC time is not over, but the POC time is more in the past than in the future. So we are really going into the very interesting development step of the company of being not a project-based company, but being a product-based company. And this sounds easy, or this sounds like a small step, but it's not. It's really a huge thing for us, and we are really we really want to do this in a excellent or in a very good way. So I would say experience in embedded software and maybe also hardware developments is a key, and this is something we are really looking for. Perfect. Okay, yeah, thank you also very much. If you have questions afterwards, want to talk to me, I will be here in the lobby area, and otherwise, please drop me an email. I would be very happy to get in touch with you.
If you found this video informative, make sure to subscribe our channel. Click the thumbs up if you liked it, or leave us a comment on what we could improve. If you are looking for a job in the embedded industry, or you've got one to offer, drop us a mail to jobs@embo.io. That's jobs@embo.io. And we'll make sure that you match up. My name is Stefan Bückelmann, and as long as you keep watching, we'll keep covering the internals of the embedded industry.